Let's look at the next passive device, which is nothing but capacitors. Second to resistors, capacitors are the next most used component in the electronics industry. Capacitors find uses in all types of circuit, from logic circuits to power supplies and radio frequency circuits to audio ones. In addition to this, there are many types of capacitors, but despite their differences, they all rely on the basic concepts of capacitance. Capacitors are components that can store electrical energy. They can be charged up with the energy from a battery, then return that energy back later. The capacitance of a capacitor is a measure of how much energy or charge it can store. In its simplest form, a capacitor consists of two separated metal plates with air or another non-conductive material filling the gap. The bigger the plates, the bigger the capacitance. To stop the capacitors becoming impractically large, they can be rolled up. Another way of increasing the capacitance is to put up some non-conductive material between the two plates. So, this is called a dielectric material. So, let us look at the symbols for it. The standard unit for capacitance is farads. Generally, the values of capacitors available will be in the order of microfarads, picofarads and nanofarads. The symbol of a capacitor is as shown. The capacitance of a capacitor is directly proportional to the area of the plates and is inversely proportional to the distance between the plates. Also, higher the permittivity of a material, higher the capacitance will be. The permittivity of a medium describes how much electric flux is being generated per unit charge in that particular medium. If we pump electrons into negative plate, electrons are repelled from the negative plate. Since positives do not move, a positive charge is induced. Higher the potential difference, the more charge is crowded onto the negative plate and more electrons are repelled from the positive plate. Therefore, charge is stored. The plates have a certain capacitance. The flow of electrons onto the plates is known as the capacitor's charging current, which continues to flow until the voltage across both the plates is equal to the applied voltage. At this point, the capacitor is said to be fully charged with electrons. The strength or rate of this charging current is at its maximum value when the plates are fully discharged and slowly reduces in value towards 0 as the plates charge up to a potential differences across the capacitor's plate, which is equal to the source voltage. The amount of potential difference present across the capacitor depends on how much charge was deposited onto the plates by the work being done by the source voltage and also by how much capacitance the capacitor has, and this is as illustrated. Let us look into the capacitance of a capacitor. Capacitance is the electrical property of a capacitor and is the measure of capacitor's ability to store electrical charge onto its two plates with the unit of capacitance being farad, which is abbreviated as F. Capacitance is defined as being that a capacitor has the capacitance of 1 farad when a charge of 1 coulomb is stored on the plates by a voltage of 1 volt. So, we can write from this definition capacitance C equal to charge, which is nothing but Q, into voltage, which is nothing but V. So, Q is nothing but charge in coulombs, C is capacitance in farads and V is the potential difference in volts. The capacitance depends on area, separation of the plates and the dielectric. In a capacitor, an electric field is formed. If the electric field is too strong, the dielectric will break down and a spark will jump. The maximum voltage is known as the working voltage. Capacitor charging and discharging. It is also possible to look at the voltage across the capacitor as well as looking at the charge. After all, it is easier to measure the voltage on it using a simple meter. When the capacitor is discharged, there is no voltage across it. Similarly, once it is fully charged, no current is flowing from the voltage source, and therefore it has the same voltage across as its source. In reality, there will always be some resistance in the circuit, and therefore the capacitor will be connected to the voltage source through a resistor. This means that it will take a finite time for the capacitor to charge up, and to rise in voltage does not take place that instantly. It is found that the rate at which the voltage rises is much faster at first than after it has been charging for some while. Eventually, it reaches a point when it is virtually fully charged and almost no current flows through it. In theory, the capacitor never becomes full, that is, it never becomes fully charged, as the curve is asymptotic. However, in reality, it reaches a point where it can be considered to be fully charged or discharged and no current flows further. Similarly, the capacitor will always discharge through a resistance. As the charge on the capacitor falls, so the voltage across the plates is also reduced. This means that the current will be reduced, and in turn the rate at which the charge is reduced, it also falls. This means that the voltage across the capacitor falls in an exponential fashion, gradually approaching towards the zero. The rate at which the voltage rises or decays is dependent on the resistance which is present in the circuit. The greater the resistance, the smaller amount of the charge is transferred, and longer it takes for the capacitor to charge or discharge. So let us look at energy in a capacitor. When we charge up a capacitor, we make a certain amount of charge move through a certain voltage. We are doing a job of work on the charge to build up the electric field in the capacitor. Thus, we can get the capacitor to do a job of a useful work. So let us look at the energy stored in a capacitor. It is given by E is equal to half CV squared. So let us look at capacitors in series. So series combinations, how it works. Charge of every capacitor is Q. The voltage of total number of capacitors in series is V1 plus V2 plus V3. The value of the combined capacitance is. So let us look at capacitors in parallel. So capacitors in parallel have a common voltage supply across them, giving Vc1 equal to Vc2 equal to Vc3. Parallel capacitors, the equation C total equal to C1 plus C2 plus C3, and it all continues until the number of capacitors which are connected. Capacitor types. When we come to the capacitor types, there are three major types of capacitors, which are ceramic, electrolytic and tantalum. Ceramic capacitors are small in size and value, ranging from a few picofarads to 1 microfarad. Not polarized, so either end can go to the ground. Value is given by a code somewhat like that of resistors. Electrolytic capacitors look like small cylinders and range in the value from 1 microfarad to several farads. Very inaccurate and change in the value as the electrolytic ages. Polarized, cathode must go to the ground. Cathode is marked with a minus sign on the case. The value is usually written on the case. Tantalum capacitors are similar in size to the ceramic, but can hold more charge. They can hold up to several hundred microfarads. These are accurate and stable, but they are relatively expensive. Usually polarized anode is marked with a plus sign.